Howdy, and welcome back to Waco Family Medicine Point of Care Ultrasound Curriculum. As a reminder, here are some icons you'll be seeing throughout the presentation today to keep your mind focused on what it is we want you to take away from this. Today's lesson is in ultrasound physics. And this is a big topic, so we're going to be dividing it up into two parts, and we'll go over each of these in a little bit more detail in the minutes to come. Now, when I said physics, I know a lot of you kind of felt like this. And don't worry, I did too. When I first started learning ultrasound and realized how much physics was, or could be, involved, I had a little bit of a panic attack. But my goal is to break it down for you in a way that's digestible, intuitive, and hopefully not put you off against the idea of using this technology in your future careers. So let's just start with the term ultrasound. What does it mean, or why do we call this type of sound ultrasound? Well, it comes from the root ultra, which means beyond, and refers to all of the sounds that occur beyond the limits of human hearing. So although we can't hear it, this is still sound, and it behaves the same way as other sounds that we are able to hear. And in fact, the acoustic spectrum extends not only beyond what we can hear, but extends beyond it in the other direction too, meaning infrasound, where whales, rhinos, elephants use lower frequency sounds that we can't pick up to be able to communicate with another or do the other things that animals need to do, I guess. So we can intuitively think about ultrasound the same way that we do electromagnetic waves, which we might be more familiar with. Things like UV rays, X-rays, gamma rays. And just like those light rays have different wavelengths and different energies associated with them, the same thing can happen with ultrasound. And the higher our frequency goes up, the more energy will be imparted into the body or the tissue that we're ultrasounding. On average, the medical ultrasound relies on frequencies of sound occurring between 1 and 15 megahertz, which is the same thing as 1 to 15 million hertz, or cycles per second. And so you can even go higher than that if you utilize different modalities that might be trying to impart a lot of mechanical energy to break up stones or to kill cancer cells. And so thinking of this and remembering that this is a spectrum will be important as we go along down through our physics lesson. So explaining ultrasound and explaining the physics behind it can get really complicated. And so if I was going to give you one key slide, and you'll notice that little key symbol there on the left, to remember, to understand what I want you to take away from this, this is that slide. In the most basic of terms, ultrasound relies on wave generation, wave propagation, wave interaction, and then wave signal reception and processing. So crystals and electricity have to come together to create mechanical energy in the form of sound waves. The sound waves have to leave the transducer and travel through the body. And then when they're in the body, they interact with other structures that they come into contact with, whether that's bone, whether it's muscle or tissue of some sort. And at those boundaries where the sound has to make a decision about reflection or traveling back or moving in a different direction or imparting its energy, that's where we get the echoes that cause the ultrasound machine to give us an image. Those reflected sounds get detected by the probe, and then a whole bunch of math and science stuff happens in the computer so that an image can be generated. Understanding each of these will later on help us understand how to troubleshoot when we're not getting the image that we're trying to get or something funky is happening on the screen. Now, it is important that we pause briefly just to discuss the differences between electromagnetic radiation, which you may know about, and longitudinal or sound waves, and the properties that separate them or make them different. Although we'll talk a lot about waves, most of us think of waves in the way we think about X-rays or light waves. And there's a lot of similarities, but there are a few key differences. So let's start with the electromagnetic waves. Electromagnetic waves are often self-propagating, meaning you could initiate one and it's going to continue forever and forever and forever until it interacts with something else that causes that energy to be dissipated in some way. They don't require a medium to propagate. So if you shine a flashlight in space, that light is going to continue into infinity through the vacuum of space until it interacts with another substance. The major bioeffect of electromagnetic waves is radiation, and we know this very well in the medical world in terms of ionization and the side effects and biologic effects that that can have. Electromagnetic waves also travel in a way that particle motion travels perpendicular to the wave motion. So if you look at this diagram, you can see that the magnetic field and the electric field are both separate. So the magnetic field is happening in a 90 degrees from the way that the particles are actually traveling in the electric field. And speed serves as a constant. We've learned that in high school probably, that the speed of light is a constant, and you can use that to then calculate E equals mc squared and all of the other things that you learn in physics. Sound waves, however, do not self-propagate. They require a medium, and eventually, because they have to travel through a medium that imparts forces onto the sound wave itself, you're going to lose energy through the process of its transfer. So sound waves will not continue forever. Eventually, they will be turned into heat and be absorbed. The major bioeffect from sound waves entering the body is mechanical, heat generation. And so that's important to think about when we use high frequency, lots of energy waves in the body. We are imparting heat. We need to be aware. And then particle motion is parallel to wave motion. So as you can see in the diagram above, although the direction of the sound wave is moving to the right, the particles are also moving to the right. And unlike electromagnetic waves, where speed is a constant, with sound, our frequency is a constant, and the speed at which that wave travels through the body will vary depending on the type of tissue it's passing through. You might have heard that sound travels differently through water than air, and we'll talk a little bit about why that's the case when we get to our section on propagation. All right, so first, let's talk about how we make ultrasound waves and what vocabulary we use to describe them. Generating ultrasound waves relies on the piezo or piezoelectric effect. I've heard it pronounced both ways, and I don't care which one you use as long as you understand it. And the key to understanding it is to focus on the animation that's on the right half of the screen here. The piezoelectric effect is a phenomenon where certain materials, most commonly we refer to these as crystals, but it can also be ceramics or polymers or a variety of different things, react when mechanical stress is applied to them. So you can see these two plates are kind of being pushed together, demonstrating mechanical stress being imparted onto this crystal. And what happens when this occurs is that there's a small, though mighty, electric voltage that is generated. And then conversely, the same thing is true. If you applied an electrical voltage to the material, it would deform or vibrate, and that would create a mechanical energy. This effect is due to the way the atoms are arranged inside the material. So you can see here with this quartz crystal, we have silicon and oxide that are both arranged in this tightly isoelectric format, I guess is how you put it. It's neutral, all the charges are balanced, but then the second that you apply a mechanical stressor, all of a sudden you get this dipole generation where some of those charges are a little bit out of whack. And this displacement causes the generation of an electric field, and vice versa. If we applied an electric field, which is what we do with our ultrasound transducers, you get a small mechanical displacement, which over time could result in the generation of a sound wave if you applied enough of it at the right energy levels to generate sound. This phenomenon is used in a variety of different applications, not just ultrasound. So we use them in sensors and actuators, but we definitely use them inside our transducers. And it's key that we understand this because this is how we convert mechanical energy to electric energy and vice versa, which enables ultrasound to be a great medical diagnostic tool. And then a fun piece of trivia is that the piezoelectric effect was first accomplished or first demonstrated by the Curie family, the same family that gave us Pierre and Marie Curie. In fact, Pierre was one of the two scientists credited with this discovery, although it had been postulated and theorized prior to his demonstration of it. So to be able to describe waves, we need to have a common vocabulary. And so the next few slides are going to be focusing on each of these words and how we describe waves using them. to put us in the right mindset for this, I want to use the analogy of watching waves go by. And this is one place where I did that in the Galapagos Islands. There's a rock over here. This is called Pinnacle Rock, but our guide that was talking to me when I visited kept referring to it as the lighthouse. And I think that we can use that analogy to help understand intuitively the ways that we can describe waves. So using our analogy of a lighthouse, imagine you were standing on a rocky lighthouse out in the middle of the ocean, watching waves pass you by. You could make a variety of different measurements to help describe those waves to somebody else who wasn't watching them with you. For example, you could see how long it takes between two waves to pass you by. So starting when one wave was passing, starting a stopwatch and counting to see how long it took until a second wave came. And that would be a numerical representation of the period of a wave. And that refers to the time it takes for one wave to pass a given point, measured in time. Now, similarly, you could also stand at one point, measure for a set length of time, and see how many waves passed in that period of time. And that would be the frequency of the wave, which arguably is the most important metric by which we describe ultrasound waves. So both of those are measurements in time. But what if we wanted to make some measurements using distance instead of time? Well, we could definitely do that. So let's say we grab a ruler and we measure the distance between two subsequent peaks of waves. That would give us the wave's wavelength. And while wavelength is something we may be familiar with when we talk about visible light and the rainbow and spectrums of light as they interact on the electromagnetic spectrum, it's not necessarily as important when we talk about ultrasound waves. And that's because ultrasound waves are much more defined by their frequency than they are by their wavelength, which can often change. Now we can also make a measurement of the displacement of the particles as the wave travels. So on this wave, we would measure from the top or the crest of the wave down to the trough or the bottom. But remember that this is a transverse wave that's depicted here on the slide, and that ultrasound waves are longitudinal waves. And so amplitude, while it is a distance measurement, really doesn't give us the full picture of what we need to understand about ultrasound waves, which is more going to be covered on the next slide when we talk about intensity and power. Now, while we've described waves using wavelength and frequency and period and amplitude, it's important to remember that the types of waves that we're dealing with in ultrasound are longitudinal waves, meaning that the particles moving in the wave as it travels through a tissue are moving in the same direction. And I think this animation really shows that well. And so we can understand how as this wave travels through a tissue, it's creating periods of pressure, periods of energy that it's being imparted. And we can see that represented here as the areas of pressure or areas of density that are created as the sound wave travels, as opposed to the lighter or less dense areas of rarefaction that occur. And it's important that we understand this so that we can understand the safety profile of ultrasounds. We describe this pressure, this energy that's transmitted into the tissue as either the intensity or the power. Intensity being this energy divided by the area over which the intensity is occurring, or the area over which the ultrasound beam is being imparted into the body. And so the larger the area, we divide that energy and apply it over a wider space, thus causing less damage at the individual small levels. Versus power, we can measure that same amount of energy, but as a function of time. We see, if we ultrasound someone for 15 seconds continuously, how much mechanical energy is being transmitted into the body, and we use power to make that representation. Now, we've been talking about waves as a continuous wave, which is important and does play some role in ultrasound, but it's equally important to understand that the majority of times that we're holding an ultrasound probe, there's actually no sound being emitted. And the analogy I like to think of for this is bats. So we all know that bats use ultrasound to echolocate or to navigate through through the night sky to be able to catch bugs and whatever else that is that they hunt for. So imagine a bat that instead of just emitting a little chirp and then being silent and listening, what if they were continuously just screaming, "Ee!" and flying through the sky? They'd have no way of knowing they were going, right? They wouldn't hear any of those echoes that were coming back. So instead of getting a nice juicy beetle for dinner, they'd instead get splattered against the oak tree I planted in my backyard. And that would not be super fun. So the same thing happens with ultrasound. With ultrasound, we have this pulse that's being emitted by the transducer and sent into the tissue, but the majority of the time, no sound is being emitted, and instead that same portion of the ultrasound probe is listening, waiting for those echoes to come back so that it can help us map and know exactly where we are in the tissue. Now, this kind of simplifies things because instead of just having one little transducer inside the probe, there's actually hundreds of them. And these are going off in a variety of different ways and different patterns to help us get the clearest images possible. But as a basic rule to understand, pulse echo ultrasound means that we emit a pulse, we then wait for those echoes to come back, and then we emit another pulse. And we can change some things on the machine to change the distance and the time it takes between those pulses or how strong those pulses are and all that stuff. But really, that's beyond the scope of what I expect you all to know. So we've talked about wave generation, but let's talk about how waves move through the human body. There's a lot of information on this slide, but you'll see the keys near the things that I want you to remember. Sound waves move through the body not at a constant speed, but instead at a constant frequency. And the speed through which they pass depends on the type of tissue that they're passing through. So we've all heard the fact that, sound travels faster in water than it does in air. And that's because of the elasticity of water. Water is much less compressible than air is. And for that reason, sound travels much more quickly through it. For the same reason, it's faster in solids rather than it is in liquids and in air. But the fact is our bodies are not made of all of the same material. If it was, we'd just be piles of goo. But we have bones and we have muscles and we have fluid, we have vessels. All of these things transmit sound waves slightly differently, and that's helpful for us because at the barriers between different areas, so between a muscle and a tendon, between a nerve and a tendon, between a vessel and a bone, all of these boundaries are where echoes are generated to come back up to the machine to be detected and represented on our screens. So tissue boundaries are what create echoes, and the strength of those echoes are translated into the brightness with which we view them on the screen. So stronger echoes, stronger reflections of that sound energy result in increased brightness on our image. And then lastly, it's important to remember that as the wave travels, some energy is transformed into other forms of energy. The machine does some calculations that helps compensate for that, but we'll spend an entire time in our next lecture talking about artifact and how artifact is generated, understanding these principles that energy is sometimes reflected or absorbed or scattered, and that affects the quality of echo that we get back. I mentioned that sound waves travel differently through different tissues because of the factors inherent to that tissue. And that's a way to sort of summarize this idea of something called acoustic impedance. Acoustic impedance is like the friction through which waves have to travel. So, if you were walking through sand or through mud, you're going to be a lot more slow than you were if you were going to be running on a track or on the sidewalk. In the same way, the sound waves travel differently through different properties because those properties have different impedances. And the impedance values, while you don't need to necessarily know them, you should know that general rule that certain tissues pass sound waves more easily, things like hollow fluids. And we'll revisit this in our next section. And then remember that ultrasound echoes reflect and refract at the interfaces between the media with different impedance values. So this is a summary of what we already discussed on the previous slide, but it's super, super important to understand where those echoes are being generated and why, so that we can understand then when things go wrong or when things go into an artifact, how we interpret that artifact to make a diagnostic image for our patients. So, woof, that was a lot of physics. We're about to get into some of the more fun stuff in our second lecture, but I want you to take a little break, kind of process everything that we've learned, and enjoy this picture of my sweet baby boy Doppler. So, as a summary, what we've talked about already is an introduction to ultrasound, differentiating between electromagnetic and sound waves. We talked about piezoelectricity and how it generates the sound waves that go through our body and ultrasound mechanics. And then we talked about how sound waves move through tissues. And then our next physics lecture, we're going to talk about how it interacts with all of the things that happen inside the body to generate the image that we need. Look forward to seeing y'all then.